Hello, everyone, and welcome to our talk, Incorporating a Machine Learning Research Project into Game Audio Production, the ExFlowSions case study. My name is Mónica Villanueva, and I'm a research engineer at SID working with generative models.
Hello, my name is Jorge García, and I am a software engineer from the Tools and Technology Audio team, currently on rotation with the SID team.
This work has been conducted at SID as part of the rotation program. In case you don't know the team, SID stands for Search for Extraordinary Experiences Division, and it is an applied research and innovation group within electronic arts, where we explore, build, and help define the future of interactive entertainment. Today, we are going to split the presentation according to the areas we have worked on most, and we'll start with an introduction to ExFlowSions, followed by a motivation of why having a tool sitting between research and production it's a good idea. Then we will share some design and implementation details. We'll have a live demo, and we will prove the validity of this tool by sharing some of the feedback we got with you. We will finish sharing some future steps and some takeaways. ExFlowSions started as a master thesis project carried out by Sergey Andreu, supervised by me in collaboration with DICE, who are the creators of the game franchise Battlefield. This is a machine learning model based on normalizing flows, but trained on a really small data set of about 10 minutes of explosion sounds. The goal of the model is to generate variations given an example, but it also performs style transfer from any type of sound effect to explosion sounds. We have published this work in an external conference, so if you would like to have more information or details about the model, feel free to check our paper. But the main idea is explained here with this figure from the image domain. So we take the sound and pass it to a low dimensional representation where a lot of details are lost. Now the model is able to hallucinate those details when taking back the sound to the high level representation. And now I'm gonna share some examples of how our model works. This is our model trained at 48 kilohertz, and we will use both in distribution and out of distribution explosion so that you can see that the model generalizes. In this case, the in distribution explosions are sounds recorded by DICE, but that were not in the training data set. So let's hear an example. This is the original sound from which we want to generate variations. And these are examples of the variations generated by our model. As I said before, the model generalizes well to out-of-distribution examples. So in this case, this is just an explosion sound downloaded from the internet. Let's hear the original sound first. And the variations. So you get an idea. And here is a sneak peek of our tool. As you can see, it's not that different from this diagram that we showed during the conference, where we have here our input sound, our output, or the variations generated by the model, and the model itself. In our tool, we have a drop-down menu where the users can choose between several pre-trained models that were trained with different parameters or under different iteration lengths. The users can also choose the temperature of the input. And now I will pass the mic back to Jorge to talk about the motivation for the tool.
Thank you, Mónica. So why create a tool for this model? Well, as we believe, having a tool sitting between research and production is valuable. So we wanted to put the model into the hands of the audio designers and evaluate its audio quality more easily. Moreover, we wanted to investigate what are the possibilities of integrating the model into production. And additionally, we wanted to offer a tool that can be used creatively and explore alternate use cases and future requirements. So we interviewed 5 power users for the requirements gathering and validation. They all wanted a tool that is easy to use, and it had to work on Windows, the main development environment that the designers use for creating the games here at EA. During interviews, we also clarified the input and output format, in this case, WAV at different bit depth and a sample rate of 48 kilohertz, which was the initial requirement for the model coming from the research phase of the project. And also during interviews, we found that the users had an important ask that was multi-channel support of stereo and above channels. This was important for them in order to use the output of the model in production. And also, on top of GPU inference, we were also discussing having CPU inference for designers and users that didn't have compatible graphics cards. So at the beginning of the project, we also started working from a research code base and had to carry out some refactoring and fixes in order to use the model inference in the tool. This original code base included various code experiments, some of them unused. So that caused that some code needed to be refactored for production use. For instance, adapting different parts of the code to be packaged as Python modules, and also consolidating some naming conventions in the code base, as well as migrating to a newer PyTorch version and doing updates, for instance, for having half precision support. And this is how the tool API looks after the refactor. We have 3 functions that are used by the tool. The first of them is the model initialization. This is going to change and needs to be recreated every time that the user selects a different model configuration in the tool. Then we have the data loader that has to be also recreated every time that the audio input changes. And finally, the synthesize single variation, or the synthesis function, I would call it here, takes as input parameters amongst various configuration and debugging options, the model configuration and the data loader that have been instantiated by the previous API calls. And now it's time to talk about the tool design. Over to you, Mónica.
Thank you, Jorge. So when working with machine learning models, there are several considerations that we have to take into account. These are not a one-fits-all, and it will depend on your use case. But we wanted to expose here some of the most outstanding choices that we had to consider for our tool. First of all, the hardware support. As we've mentioned before, GPU inference would speed things up, but maybe not everyone has the appropriate hardware, especially if we consider a local execution environment. This is not a problem if we are using a server or a cloud solution. But also we have to think about how we're going to deliver the tool to our users. We decided to go with a local execution environment, so we are employing the hardware from our users directly. And that means that we do need to implement CPU support in case they don't have the required GPU graphics card. We also decided to go with an executable as a form of delivery in order to simplify the way in which the users access the tool. That way, they don't have to deal with installing dependencies or Docker images. But this also raised the question of where do we store the model weights? Bundling the weights together with the tool has several drawbacks, including the increased size of the tool itself. What we decided to, there's another one, of course, that if the model and the weights were to be linked together, that would be a security risk. We finally decided to use DVC, which is a data version control open source library, which allows us to store the weights in a remote storage solution and bundle in the tool only the DVC files, which basically just point to where the weights are stored. We are also using as the remote storage solution Google Drive, and this allows us to control who has access to download the weights, but we can also take advantage of their authentication pipeline. This might not be a perfect solution, but it's working pretty well for us at the moment. And now I will pass it back to Jorge to discuss the front end.
Thank you, Mónica. We evaluated different framework alternatives and narrowed it down to a couple of them, which is Gradio and Streamlit. We decided to use Gradio because of several reasons, amongst them the availability of audio components, like the audio player, the features of the framework, and the easiness of use. With Gradio, we were able to write all of the UI in Python, so there was no need to write any wrappers for the ML model from other programming languages, which saved us time. We were also able to do rapid prototyping and customize some parts of the UI. Gradio has some cons and limitations, though. We found some issues with certain browsers where the microphone input wasn't working properly, and there wasn't also any available event when downloading the audio outputs, which we wanted to use for telemetry. And also, the Gradio version we wanted to use was broken for the audio input with some configurations and browsers, so we had to downgrade to a previous version. Before starting to implement the UI, we created a tool prototype in Figma. In case you haven't heard of Figma before, it is a software where you can create mockups, wireframes, and prototypes for any type of application. So we used it to validate the initial approach and the requirements. And we also used some of the artwork we created with Figma in the tool, like this branded header that you can see in the screen capture, helping us deliver a simple yet functional and appealing user interface. Additionally, we created a short testing strategy document covering manual testing, unit testing, and testing automation. For the manual testing, we defined 5 test cases covering the hot paths of the tool, like the inference process and the model configuration parameter changes. For the unit testing, we wrote 7 unit tests with a broad coverage for testing the UI parameters, synthesis mode, and input modalities like mono and multi-channel. And as a side note, we can also mention here that the manual testing of the microphone input wasn't covered in the unit tests. These tests were also automated and integrated within the GitLab CI pipeline that we are using for the project. And in this case, we used the radio client API for triggering and running the unit tests in the server. And now it's time for the demo.
Thank you. We wanted to show the most important features of the tool in a demo. So we're going to show the normal workflow where a user just uploads a sound to the tool and generates variations. But we are also going to show how to change the configuration to modify the results, and the microphone recording that pairs very well with the style transfer capabilities of our model. So just for reference, these are the sounds that we are going to use. And now Jorge will start with the live demo. So we're setting things up here a bit, changing the screen. Perfect.
Okay, so in the repository, or basically the location where we have stored the releases of the tool, we have a way to download a zip file. So the user has to do that and then uncompress it locally. And afterwards, they will see the files that we have here on the screen. And what I'm just going to do is what the user will do normally is to double click the ExFlowSions executable. Then it will start from a big window in the background, doing different initialization and setup for the tool, like caching the models. And then the authentication stage and pipeline will start. What I need to do here is just to select my username and account, check all and grant access to DBC to my Google account as well, and click on continue. And then after this, and hopefully after just a few seconds, the tool will start in another tab of the browser that I have opened. Okay, it has opened now. What I'm going to do is to go full screen for easiness of use, and then just setting things up so that we can see it clearly. And for the first part of the demo, what I'm going to do is to load one of the sounds that we got from the DICE dataset. In this case, it's an explosion sound that has 2 channels, stereo file. If we double click on the sound, then it will show in the audio component that radio provides different information. We have added here also for clarity and for easiness of use, the number of channels, the sample rate of the sound, and the name of the file name of the sound that has been loaded. So for the first part of the demo, what I'm just going to do is to leave all the configuration parameters as default, and then click on synthesize. And then Mónica is going to explain what each of the parameters do.
As I mentioned before, we have this model configuration where the user can select between several models that have been pre-trained. And then we also have the temperature parameter. So this parameter is pretty common in generative models. In our case, we are using a normalizing flow. How this is trained is that we take the input sound and we convert it, or the data set, we convert it into a normal distribution, so that when we invert the model, we can just sample from this normal distribution in order to reconstruct the sound. And we will see later what's the effect of changing the temperature.
Okay, so for sake of comparison, what I'm going to do first is to play the original sound, and then we will hear the variations. Great. Now for the next part of the demo, what I'm going to do is to reduce the number of variations to 1 to speed up things up, and then set the temperature to 0.6. Also, Mónica is going to comment on this.
So what we are doing by reducing the temperature is also reducing the width of the normal distribution. So what we are doing is basically sampling closer to the mean of the distribution. And that should have a result that is more consistent, but potentially more realistic.
Again, I'm going to play first the original sound, and then the variation with this temperature value. Great. So now the next part of the demo is going to use a different model configuration, in this case, medium quality and high variation. And just, I'm going to revert back to the temperature to 1.
So what high variation means in this case is when we were developing the model, we saw that if we reduce the low dimensional representation, the model had more freedom to create more variations, but it also decreased a little bit the quality of the sounds. And we will hear this now.
Again, just going to play the original first. And now the variation. As we can notice, the tail of the sound in this case is noisier in some way because of what Mónica explained. Great. So what I'm going to do, just to go into the next stage of the demo, is to go back to the original model configuration. I'm just going to leave the temperature as it is, the number of variations as well, and then we are going to record with the microphone. And when you're ready, Mónica?
Yes.
Just click on record. Then we are going to synthesize, and in this case, this will showcase the style transfer feature of the tool. And if you have noticed, there was also a warning on the screen. This means that there was a difference or a mismatch between the input sample rate and the output sample rate. In this case, because we are recording with this laptop, the input sample rate is 44.1 kilohertz, and the model sample rate is 48 kilohertz, as we said at the beginning, so we need to sample the result. So let's hear how this sounds. So first with the recording from Mónica. And now with the style transfer applied. Great. We also have some other demos that showcase the style transfer feature in multi-channel. We can also share them with you if you are interested as well, but for the sake of brevity, we are wrapping up the demo and continuing with the presentation. So we created a feedback form and asked a set of questions covering tool UI and usability, model quality and performance, and tool value and impact. And we also had an open feedback question for the users of the tool. So if they wanted to say something that wasn't covered in the previous sections and questions of the form, they were able to express themselves and maybe just give additional feedback or more details if they wanted. Here's the feedback analysis of the results and the feedback we got from the form, from the 5 power users that we mentioned at the beginning of the presentation. So about the easiness of use, most of the responses said that the tool was easy or very easy to use, while getting good sound results wasn't very easy at all. The audio quality of the results were also mixed between high and average. And to the question, what are the time savings and positive impact this tool could bring to your audio workflows, most of the users scored the tool in the middle range. On the other hand, most of the users tried out the majority of features available in the tool, and also the majority of them said that the tool has fulfilled their initial requirements and expectations, which is great. And now diving a bit deeper into the feedback analysis, we have cherry-picked here some of the positive comments and areas of improvement. Again, it's worth noting the positive feedback about the user interface and easiness of use as well as the sounding results using the default settings. In terms of areas of improvement, some of the users said that the potential of the tool is very high, but they wouldn't use it in its current form. They think the quality of the model for variation creation isn't there yet. And now back to Mónica to talk about future work and conclusions and takeaways. Thank you.
Thank you, Jorge. So from our own experience with the tool and the feedback we have received from the users, we have identified several areas of improvement. The first of all would be to improve the time it takes to perform the first inference, which is way longer than for the rest. And this is probably due to synchronization issues between hardware. We also want to improve the flow of the interface by performing several tasks either more responsibly or in the background. For example, loading the different models or the data loaders, or giving a better way for the user to stop an inference job that's already started. We also want to implement several quality of life features, for example, downloading all the generations at the same time. Additionally, one of the most requested features is to train custom models. But in order to do that, first, we need to make sure that the approach is robust enough to work with different sound effects. We need to streamline the way we train the model, and we need to inform our users about the legal limitations of training with their own sounds. We are also experimenting with using telemetry to gather passive feedback. As you can see here, this is our work in progress, but working prototype for telemetry. We are using HR insights, and we are gathering information like the number of users, different types of telemetry events, including exceptions, so that we know when the application is not working. And also from a research point of view, we are also recording the users' favorite models so that we know which versions of our models are working the best for the users. And as you can see here, this is just a debug dashboard, but we will include telemetry in production for our next tool release. And this marks the end of the presentation, but we want to finish with some takeaways. As we mentioned before, there are multiple benefits about having a tool that sits in between research and production. From the research point of view, it helps validating research that has been done in isolation. It facilitates gathering feedback from your target users, and it provides a framework for quick iteration, experimentation, and improvements. But there are multiple benefits as well from the production side of things. So it helps learning of research that can be helpful early on. It allows developers to influence that research and promotes early adoption. And it provides also a starting point to integrate this technology further into production workflows. We also wanted to highlight some learnings and challenges. This is probably very personal, but we feel like we have expertise both in tooling and machine learning, so it should be pretty interesting from those points of view. So the learnings we take with us is that Cravio allowed us to prototype an interface very quickly, and it would have supported as well remote backend if we would have decided not to go with a local executable. We develop a workflow that is easy to use with minimal overhead to our users, and also accounting for some security measures. And we were glad to discover the quality of the feedback some of the users gave us, and the willingness of some of them to keep in the loop and be involved in the future of this research. On the other hand, we had several challenges, which included event radio. As well as it worked, there were some bugs that affected us directly and for which there are no current solutions. And there are some problems as well if you want to do some advanced things that are not supported by the current API. For example, we wanted to have a telemetry event when the users were downloading sounds, but there are no handling events or listeners for the download button. Gathering requirements, it's also tricky. If you've ever developed software for some external client or some different people have different concepts of and definitions of concepts. The requirements might also change during development, and it's always a challenge. Also, improvements and iterations can be affected by the amount of users you're dealing with and their availability to test and get feedback. And all of this is magnified by limited time. This could be, for example, a tight deadline to deliver, or in our case, the duration of the rotation program. Finally, we wanted to take this opportunity to help the people, to thank the people that have helped with the development and the users that gave us requirements and feedback. And of course, all of the SIG team for their support and helpful discussions. That's all from us, but we have some time now to take any questions you may have. You can also reach us after the presentation or mail us directly to our mail accounts. So thank you for your interest.
Thank you.